everyone, welcome back to the Space Koala, your favorite channel for all things astrophotography. My name is Lusa, and today we're back with another deep dive session, this time tackling a question that many astro enthusiasts ask, or should ask, which is, are fast telescopes really better? Spoiler, not always. With so much marketing hype around fast astrographs, it's time to set the record straight. Fast telescopes are all the rage. This is on the website of Celestron. Since it is an f2 optical system, imagers can use shorter exposure times to capture detail in faint objects. While I love to use my native f2 telescope to capture faint objects, I love to use my native f11 telescope to capture faint objects just as much. Once we understand what happens to the light entering the telescope, it turns out it doesn't make that much of a difference. First, let's talk about what a focal ratio is. We can describe a telescope really well just by its aperture and its focal length. The first one, aperture, is essentially the diameter of the lens or the mirror, and it defines how much light is being collected. The second, the focal length, defines our magnification or the field of view, if you will. The focal ratio, or f number, is simply the ratio of these two numbers. It is the product of a simple mathematical division, and it adds no additional information whatsoever to the other factors already described. Let's see an example. A telescope with a focal length of 800 millimeters and an aperture of 200 millimeters has a focal ratio of f4. 800 divided by 200 is 4. A telescope with a focal length of 1600 millimeters and an aperture of 200 millimeters has a focal ratio of f8. 1600 over 200 is 8. A telescope with a focal length of 1000 millimeters and an aperture of 250 millimeters has a focal ratio of f4, as 1000 divided by 250 is 4. Again, the focal ratio is a simple calculation. However, it seems to have a huge impact on how we perceive and use our telescopes. It seems like sometimes we even give it a larger significance than we should. So now with these three different numbers that we have to describe our optics, we have to ask ourselves, what is then a good way to compare two telescopes with different focal lengths, diameters, and f numbers? One way to think about it is to compare how the telescopes perform when trying to obtain the same exact image, meaning the same field of view and the same image scale. If you'd like to know more about fields of view and image scale, do not miss the video that I made on this very topic, because an understanding of those concepts is really crucial to get the most out of today's video. So let's compare some telescopes. Today, for simplicity's sake, we'll be focusing on the light gathering capabilities of all the instruments under perfect conditions, perfect sky, great seeing, and no losses in the process of binning and drizzling and all of those things that we're going to see. We'll be covering three examples. We'll be comparing two telescopes with the same focal length, but with different diameters and therefore different f numbers. Two telescopes with the same diameter, but with different focal lengths and therefore different f numbers. And two different telescopes with the same constant f number, but with both different focal lengths and diameters. In all cases, the goal is to obtain the same exact image with both telescopes, both in terms of field of view and image scale. Let's start with the simplest case. Let's look at two telescopes with the same focal length, but with different diameters and therefore different f numbers. Since the focal length is the same between the two instruments, provided that we use the same camera sensor, the field of view and the image scale will automatically be exactly the same. Let's see an example. Imagine we have a slow-ish 800 millimeter focal length f8 telescope with a 100 millimeter diameter and an 800 millimeter focal length f4 telescope with a 200 millimeter diameter. If we consider light coming from a galaxy, the larger diameter, or the larger bucket of the f4 scope, collects 4 times more light than the f8 scope. In this case, the faster scope collects more light per unit of time due to its larger diameter. So faster scopes are better, right? Not necessarily. For scopes with the same focal length, the larger the diameter, so the faster the scope, the better. However, this has nothing to do with the speed of the telescope per se, and has everything to do with the larger light collecting area of the tube. So now, in the second case, what happens if the focal lengths of the two telescopes are different? Let's compare two telescopes with the same 200mm aperture, but with different focal lengths and therefore different f numbers. Once again, we'll be using the same sensor on both telescopes. Here we have an 800mm focal length f4 telescope and a 1600mm focal length f8 telescope, both with a 200mm diameter. Say we take 40 subs of 300 seconds with both telescopes using the same sensor. The number of photons collected by both scopes from a given area of the sky in the same interval of time is the same, since the light collecting area of the two scopes is the same. However, the slower telescope provides a more magnified image. The field of view is 1/4 of that of the faster scope, and the image scale is different. On the faster scope, 1 pixel of our camera collects the photons that on the slower scope are distributed over 4 pixels. As a result, the f4 telescope provides an image of the target that is 1/4 of the size as that of the f8 telescope, but it is 4 times brighter. So to effectively compare the performance of the two systems, we have to find ways to actually match the two images taken with the two telescopes to make them equivalent. There are two things we need to be matching here: the image scale and the field of view. In order to match the image scale, we either have to upsample the image of the faster telescope or downsample the image of the slower scope. In order to match the field of view, either we have to crop the image of the faster scope or we need to take a mosaic with the slower one. So between all these options, we have a total of 4 combinations we can do to obtain the same image with both telescopes. Option 1. Crop and drizzle the image of the faster scope. The first option keeps the field of view and resolution of the f8 telescope. We can achieve this by performing a 2x2 drizzle during the integration of the images from the faster one. Drizzling is a technique that increases the resolution by combining data from multiple images. By applying a 2x2 drizzle during the integration process, we can match the resolution of the f8 scope. This way, we can achieve the same resolution despite the faster scope having a lower focal length. This may lead you to think that this is proof that the faster optics are better because we can still achieve the same resolution while maintaining a brighter image. However, this is not the case. Now we are distributing the previously higher amount of light on 1 pixel into 4 parts. Therefore, each pixel will get 1/4 of the light from before, so we arrive at the original resolution and original amount of light as well. You may have seen some DSLR or mirrorless cameras that offer the option of a super resolution image. This is exactly the process that they do in camera. They reconstruct the image of the incoming light on a slightly larger grid while shifting the sensor ever so slightly. If you're interested in a more in-depth video explaining how and when drizzling should be used or avoided, stay tuned for an upcoming video on this very topic. Back to our image. Once we have this drizzled image, we can just crop the edges off to achieve the same exact photo, having spent exactly the same amount of time imaging the sky. Option 2. Crop the image of the faster scope and bin the image of the slower scope. The second option keeps the field of view of the f8 telescope and the lower resolution of the f4 scope. This time, we will still crop the image of the f4 scope. However, we will downsample the image of the f8 scope by performing a 2x2 bin. Binning combines multiple pixels into one large pixel, effectively increasing the signal while reducing resolution. This essentially does the exact opposite operation compared to the drizzling process we saw before. We crop the image from the fast scope, and this will once again match the field of view and the resolution obtained with both telescopes, having imaged the sky for the same exact amount of time. The third option keeps the field of view as well as the resolution of the f4 telescope. To match the resolution, we have to do the 2x2 binning we've seen before for the f8 telescope. However, as we would like to cover the entire wider field of view of the f4 telescope, we need to do a 4-panel mosaic of this part of the sky. As we've already seen, the telescopes collect the same amount of light from the same area of the sky in any given amount of time. However, the slower telescope only collects light from a smaller area of the sky at once, so we will have to spend 4 times as long imaging the sky to create the mosaic. So, to match the image of the f4 telescope taken in 40 times 300 seconds the slower telescope will have to spend 4 times 40 times 300 seconds imaging the mosaic. Here we can stop for a second and contemplate what we've seen so far. In the first two cases, when we were interested in a narrower field of view, the performance of both systems was identical. Therefore, there was zero benefit to using the faster system. However, where we do start seeing differences in performance is when we have to start expanding the field of view. We are slowly arriving at the conclusion that the true difference between a faster and a slower system is the field of view, not so much the speed. The final way to compare these two telescopes, for the sake of completeness, is to create the higher resolution image of the slower telescope, but matching the wider field of view of the faster telescope. In this case, we will still be doing a mosaic with the f8 telescope, but we will not be doing any binning in order to conserve the high resolution. As we are not doing any binning, the resulting image is of course a quarter times as bright, so 4 times darker, as that of the faster scope. However, to achieve the higher resolution, we have to once again perform a 2x2 drizzle on the faster scope's image, making them equally as dark. So once again, to match the image of the f4 telescope taken in 40 times 300 seconds, the slower telescope will have to spend 4 times 40 times 300 seconds imaging the mosaic. We can confirm and build upon the previous conclusion that the faster scope only ever has an advantage when we would like to image a wider field of view. Now we have seen that this is the case at every single possible desired resolution or image scale. The only thing that truly changes is the field of view. Once we focus on a given area of the sky, the speed of the optics becomes completely irrelevant because any gain in the speed is offset by a lower resolution and vice versa. So that's it. That covers all possible ways to compare two telescopes with the same aperture and different focal ratios. The only thing we haven't looked at is two completely different telescopes, but with the same constant f number. So let's do it. Let's compare two telescopes that have the same f number, but they have different diameters and focal lengths. Let's consider a 200mm f4 telescope with a focal length of 800, and then let's consider a large 400mm f4 telescope with a focal length of 1600. For simplicity, we have kept the same focal lengths and therefore the same fields of view as we did in the previous example. Therefore, to do the comparisons and obtain the same image and image scale, we can use the exact same strategies as we did before. However, this time the diameters and therefore the light collecting capabilities of the two telescopes are different. So let's see how many photons per pixel we can obtain in this configuration in a given amount of time. In this case, the larger diameter of the 400mm f4 telescope allows it to collect 4 times more light, making it truly faster to take the same images. Going through the 4 cases laid out previously, we can see that the first case, cropping and drizzling the images of the shorter telescope, will actually make the overall image darker, therefore we'd need 4 times as long to achieve the same image. Cropping the image and binning the longer telescope's image will result in the image that is 4 times as bright, therefore we'd cut down on our imaging time to a quarter of the time with the larger scope. Therefore, doing a mosaic with binning will take the exact same amount of time as using the shorter telescope natively. The larger light collecting area offsets the longer time needed to cover each part of the sky separately. And finally, doing a mosaic and keeping the original resolution also means that the shorter telescope will have to image 4 times as long to match the brightness of the longer telescope. So by comparing two telescopes that have the same focal ratio, we can really confirm that the only thing that truly matters is the light collecting area. In this case, the 4 times larger light collecting area completely made up for any time lost having to image different parts of the sky separately doing a mosaic. But now it is time for some disclaimers. As stated at the start, these comparisons were very much focused on perfect conditions. All of these calculations and statements before hold perfectly true when we're talking about the light collecting capabilities of the instruments. However, in reality, we care much more about signal to noise ratio versus the pure number of photons collected. The first point is binning is only ever so efficient on CCD sensors. Binning on CCD cameras is done at the hardware level, resulting in a true binning process. In CCD binning, 4 pixels are combined into one, increasing the signal while keeping the noise the same as we are just reading out 1 pixel, essentially. However, with the CMOS cameras that many of us use nowadays, binning is only done in software, meaning each pixel is first read out individually, and only the read out values are combined. Therefore, this is more similar to stacking them than to true binning. In CCD binning, we are increasing the signal-to-noise ratio by approximately 4, considering only the pixel size, while in CMOS binning, in the same example, we would only increase it by the square root of the number of pixels combined, so the square root of 4, which is 2. Similarly, when we're doing a mosaic, we have to have an overlap between the different panels of the mosaic. Therefore, we will always lose a little bit of the ideal field of view, unlike in the calculations we've seen before. This overlap is impossible to quantify really because it can depend on the part of the sky, the dithering settings, and the preferences of the astrophotographer. After considering all these examples, we have seen that the F number doesn't really matter that much for the most part, and a lot of images can be taken in exactly the same amount of time with a faster versus a slower system given the same diameter. However, we also clearly did see that the faster scope can sometimes have a benefit when we are trying to image a wider field of view. So surely, faster is still better, isn't it? We have everything to gain and nothing to lose by going fast, right? Not so fast. Fast telescopes have many advantages, especially when imaging large objects, but they do also come with a number of drawbacks that are not so trivial to quantify. All of these drawbacks and difficulties originate from the very property of the optics that it is fast, meaning the light rays arrive at the sensor at more of an angle. This makes them extremely sensitive. For example, if you want to be imaging with a narrowband filter with a fast like f2, f3 system, you will need to be buying specially made filters for those systems that can sometimes get expensive. The reason for this is because of how the light waves go through the filter, they can kind of shift out of the bandwidth that we're interested in, and you will end up losing your signal if you're not using the correct filter. Also, fast telescopes, especially Newtonian refractors, are much more sensitive to collimation, which means they require precise alignment tools. You can happily collimate an f8 with just a Cheshire eyepiece, or you can collimate an f4 tube with a Barlow laser. But to collimate these ever so popular f2.8 systems, like that one, you'll be looking at precision collimation tools if you would like to achieve perfect stars. For the same reason, faster optics are much more sensitive to focus. As the light cone arrives at such an angle, the tiniest shift can visibly bring the image out of focus, which can even happen in a single long exposure shot if the temperature change is happening too quickly. Fourth, due to the angle of the incoming lights, a faster system will have a smaller image circle, effectively reducing the maximum field of view obtainable. When they do have a large image circle, they also usually tend to have a large central obstruction, a large secondary mirror, which in these extreme cases can even block out a significant amount of the incoming light, effectively reducing the light gathering capability of the instrument. In these cases, in place of the F number, we can use the much more informative T number, which takes the true light collecting area into consideration rather than a simple ratio of the diameter and the focal length. Last, but definitely not least, faster telescopes have a harder time reaching and achieving the same contrast in certain higher spatial frequencies that slower optics have no problem getting. Stay tuned for a deep dive into contrast and spatial frequencies very soon. I personally use both fast and slow telescopes, like my Celestron Bressa native f2 or my Celestron C14 Edge HD, which is a native f11. I choose the instrument that I use solely based on the field of view that I would like to achieve, not based on the speed of the instrument. When I do have multiple options for the same field of view, of course, then I will choose the faster telescope, because it has a larger aperture. In conclusion, all this hype around fast astrographs is a little bit overstated, in my opinion. You should focus on the objects that you want to capture or the field of view that you need for your specific astrophotography goals, and then pick the largest aperture you can for that focal length. The speed of the telescope is just a number that doesn't tell you anything new about the instrument that you didn't already know. Thank you very much for watching. If you found this video helpful, let me know in the comments. Share it with anyone who might find it useful, and subscribe to the Space Koala to support me in making more in-depth astrophotography content such as this one. Thank you, and as always, clear skies!